Okay, now we're going to move on to graphing cubic functions. We'll do some, like we did with the quadratic functions, we'll do some general cubic examples, and then we'll move on to economic applications of cubic functions. Now, that said, we had profit functions that we maximized in the quadratic form. That seemed sufficient to be able to come up with a profit maximizing quantity level. So why are we moving into cubic functions? Believe it or not, in economics, the most realistic model for a firm is in fact a cubic profit function. And the reason that is because linear cost functions or even quadratic cost functions do not produce the typical features of a cost model that incorporate things like decreasing returns, increasing returns, in other words, increasing costs or U-shaped cost function, marginal cost functions, U-shaped average cost functions, etc. So if we have, however, if we have a cubic function, say, that looks like this, okay, so just some sort of basic cubic cost function, when we take the average, okay, in order to find our different average costs, okay, so this would be average total cost here, this would be ATC. When we divide this portion by Q, of course that would be AVC, and when we divide this portion by Q, that would be AFC. So this would be average total cost equals average variable cost plus average fixed cost. What's interesting here is that the average variable cost in particular would now become quadratic. So in this case, the average variable cost would equal Q squared minus Q plus 1. Now that's quadratic. It's also concave up, okay? So it would be a U-shaped average variable cost function. And if you remember back in introductory microeconomics, that's what we're used to seeing. We're used to seeing cost functions or cost models that look like this. And how do we get those? How do we get that sort of pattern? How do we get that sort of model? It comes from a cubic cost function. Now, that means then, if you have a cubic cost function, obviously your profit function is also going to be cubic. Okay, so that's why it's important to move this next step. And frankly, this is the next and almost final step in quantitative analysis in this course, is moving to the full-blown, full-fledged, most realistic of all mathematical models that economists use. Now, that said, we have to get a few or a couple of things out of the way with regard to actually how we come up with the critical points needed to graph a cubic function. Okay, a cubic function is going to give us a general graph such as this or this, or let's, something like this, etc. So it's going to give us something that is not going to be concave in one direction over all Q or over all X like our quadratic functions did. Our quadratic functions would be concave up for all q or all x, or they'd be concave down for all q or all x. The difference here being is that only part of this function is concave up. The other part of the function will be concave down. Now, when we determined, okay, the maximum or minimum of a quadratic function, we focused on the first derivative. We focused on f prime of x. And we would set that equal to 0 in order to find that x or q coordinate of that maximum or minimum. The problem here is there may not exist a maximum or minimum on a cubic function. There might be one. So you can imagine instead of a function that looks like this, that's nice and smooth, you can imagine this function being kind of humpy like this, lack of a better term, kind of humpy like this, okay? And in this case, it's going to have a minimum and it's going to have a maximum. So you can see how this picture can become far more complicated. But what we're going to find out is this derivative, this first derivative right here, still becomes extremely important in finding what the x or q coordinates of those maxes and mins are, okay? It's just that instead of being able to solve for x uniquely, we're going to have a first derivative that itself is going to be quadratic. So it's going to give us two values through the quadratic formula, of course, for these x coordinates for the maxes and mins, okay? Now, one thing we have to realize, and let's go back to the quadratic functions. When we had a quadratic function, we set f prime equal to 0. What were we looking for? Well, as I said, we were just looking for the maxes and mins. But more importantly, we were looking for where the slope transitioned from either negative to positive or positive to negative, okay? That was determined, that point where the slope changes was determined by setting the first derivative equal to 0. Here, in a cubic function, we're looking for where the concavity changes from either concave up to concave down or concave down to concave up. How we find that point is by setting the second derivative equal to 0 and solving for x, okay? So again, setting the first derivative equal to 0 was searching for the point where the slope changes from positive to negative. Setting the second derivative equal to 0 tells us where the concavity changes from up to down or down to up. Now, whereas we called these critical points here, we called those critical points maxes or mins. Okay, maxes or mins. We're now going to call this critical point, that is called an inflection point. Okay, inflection point. Okay, so the second derivative is going to search for the inflection point. The first derivative searches for the maxes and mins. All of these are called critical points. Now, you might find some books, and including the book we're using, talks about extreme points, and really what they're talking about are the maxes and mins. Extreme points are just a subset of critical points. All of these are critical points, and that's really the jargon that I use when I'm describing either inflections or maxes and mins.